Hi friends, I welcome you all to the last part of module 5, which is spring mass system. Actually, this is an extension of simple harmonic motion, or better to say, it is an example of simple harmonic motion. Now let us see in detail what is this spring mass system is. So spring mass system or spring mass model, let us explain it with the figure itself. We consider a vertical elastic spring which is fixed at the upper end and the lower end is free. This length is L. Now, assume that a weight is attached to this lower end. If a weight is attached to the lower end of the spring, let the weight be W. If it is attached to the lower end of the spring, what happens? Obviously, it will start moving in the downward direction. And finally, it will be reaching at an equilibrium position. So here in this figure, we can see that after a weight is attached, finally it will be reaching an equilibrium position. Let that position be represented by 1, 1. And from this point to this point, let it be represented by the letter E, where E is the extension, or better to say it as static extension. Now again assume that from this position 1 1, this weight is pulled downwards and then released. So what happens? It will be moving up and down in a simple harmonic motion, which means from this point position 1 1, it is being extended to the position 2 2, and then if it is released, it will start vibrating in a simple harmonic motion. So that's why this spring mass model is an example of simple harmonic motion. Now let us see some equations for that. First one, the period of oscillation is given by, we know it is represented by the letter capital T. So the period of oscillation is given by T equal to 2 pi into root E by G, where E is the static extension and G is the acceleration due to gravity. So this is the first equation to be studied. T is equal to 2 pi into root E by G. Or we will be making some modifications in this equation. So better to study those equations. Now static extension, we know it is the extension when the weight is attached to the spring, that is E. When weight is attached to the spring, there is an extension, that is static extension. And also one point to be noted over here is the amplitude R should be less than static extension E for simple harmonic motion to occur. We know what is this amplitude is, and static extension also we studied from here. So for occurring simple harmonic motion, the amplitude R should be less than static extension. Now there is one more term in this, which is stiffness of a spring. So stiffness is defined by weight per unit deflection, or if you are writing it in letters, stiffness is represented by the letter K, weight is represented by W, and unit deflection is represented by the letter E. So E is either unit deflection or static extension. So we can rearrange it and write it as E equal to W by K. And we already know period of oscillation T is given by 2 pi into root E by G. We are just substituting this W by K instead of E. So it is 2 pi into root W divided by Kg. Now if it is represented in terms of mass, so it is W equal to mg, just substitute over here, and finally you will be getting T equal to 2 pi into root m by K. So this is the equation which we want to study in this topic. Or frequency is, it is just 1 by T. So it is 1 by 2 pi into root K by m. Study any one equation, that's enough. Don't get confused between these two. If it is T, 2 pi will be in numerator. We have already studied T is equal to 2 pi by omega. Similarly, T is equal to 2 pi into root m by K. And there are two more equations related to this, which is V is equal to R omega and maximum acceleration is R omega square. So maximum velocity is R omega, maximum acceleration is R omega square. T is equal to 2 pi into root m by K. This thing is just reciprocal. And this equation also to be studied. Stiffness equal to weight per unit deflection. So using these four equations, or you can include this frequency also. So using these equations, you can solve any type of problems which will be coming in this spring mass system. Okay, let us see the first problem. Calculate the stiffness in Newton per centimeter of a vertical spring to which a weight of 50 Newton is attached and is set vibrating vertically. The weight makes 4 oscillations per second. So stiffness is to be calculated. weight is given 50 Newton, weight is 50 Newton. It makes 4 oscillations per second. What is this? Oscillations per second? It is same frequency. So frequency can be represented either as hertz or oscillations per second or cycles per second. So the weight is given 50 Newton, frequency is 4 oscillations per second. Now the equation connecting all this is F equal to 1 by 2 pi into root k by m, or if you are studying this equation, t is equal to 2 pi into root m by k. So time period t is equal to 1 by frequency, you will be getting 0.25 seconds. So equation is t is equal to 2 pi into root m by k. T is known to you, 2 pi into root m. Instead of mass, the weight is given 50 Newton. So convert this weight into mass. We have W equal to mg, so m equal to W by g, which is 50 divided by 9.81. K to be determined. So solving this, you will be getting K as 3216.18 Newton per meter. Why is this Newton per meter? What is the unit of stiffness? Here we can see stiffness is weight by deflection. Weight unit is Newton, deflection unit is meter. So stiffness is Newton per meter. Now all these are in SI units. This is 50 Newton, 4 oscillations per second or hertz. So finally you will be getting it in SI unit itself, which is Newton per meter. Now what we want is in Newton per centimeter. So convert this meter into centimeter. So divide this thing by 100. Finally you will be getting 32.16 Newton per centimeter. Let us see the next problem. The frequency of free vibrations of a weight W with spring constant K is 12 cycles per second. When an extra weight 20 Newton is coupled with weight W, the frequency reduces to 10 cycles per second. Find weight W and stiffness K. So in this case, there are two cases. The weight is W, then the frequency is 12 cycles per second. When an extra weight 20 Newton is coupled with weight W, which means if it is W plus 20, the frequency becomes 10 cycles per second. So here there are two cases. We will be solving those two equations and finally you will be getting the answer. So let us see. Now what is the equation connecting all these things? Frequency and weight. We have frequency equal to 1 by 2 pi into root k by m, or it is in terms of W. So instead of mass, represent it in W. M equal to W by G. So frequency F equal to 1 by 2 pi into root kg divided by W. So this is the main equation. Now the first case is when the frequency is 12 cycles per second, the weight is W and stiffness is K. So instead of frequency it is 12, 1 by 2 pi into root kg by W, let it be equation 1. Second case is when an extra weight 20 Newton is coupled with weight W, which means when the weight is W plus 20, the frequency becomes 10 cycles per second. So 10 equal to 1 by 2 pi into root kg divided by W plus 20. This is equation 2. Now solving equation 1 and equation 2, you will be getting the answer. What to do? Just divided equation 1 divided by equation 2. So after solving all these things, you can see that finally you will be getting W, which is 45.45 Newton, and substitute this W in either equation 1 or 2 and find the stiffness value K. You will be getting 26311.56 Newton per meter. So that's all. Next problem. A weight of 50 Newton suspended from a string vibrates vertically with amplitude of 8 cm and a frequency of 1 oscillation per second. Find the first one, stiffness of the spring. Second one, maximum tension induced in the spring. Third one, the maximum velocity of the weight. So what all things are given? Weight is given, which is 50 Newton. Amplitude is given 8 cm, convert into meters, so it is 0.08 meters. Frequency is 1 oscillations per second. Now what is the equation connecting this weight and frequency? Frequency F equal to 1 by 2 pi into root k by m. Instead of mass, weight is given, so convert this mass into weight, which is W by G. So frequency is equal to 1 by 2 pi into root k G divided by W. Just substitute all these values. Frequency equal to 1 by 2 pi into root k is unknown, G is 9.8 divided by W is 50. So finally you will be getting K as 201.01 Newton per meter. So the first case is okay. Now the second case, the maximum tension induced in the spring. We didn't study anything about the maximum tension in the equations, but we know that tension is same as that of load or force. So stiffness, force or load relation is stiffness equal to load by deflection. But we have studied earlier as stiffness equal to weight by static extension. So that's a particular case, total weight divided by the total extension. If you want, you might be wondering, this load is same as that of this weight itself. So that's the original thing, stiffness equal to weight by static extension. Over here it is given amplitude in terms of amplitude. So that also we studied earlier as a note. This amplitude will be less than that of static extension. So we are not going up to the static extension. This amplitude will be less than static extension. So what we want is corresponding to this amplitude, we will be finding the load or force. So stiffness is load by deflection. This deflection means it is up to the amplitude deflection, which is 0.08. Stiffness value won't change even if it is up to this amplitude or up to the full static extension. So stiffness will be same, which is 201.01. So load means it is the same as that of tension itself. So load equal to stiffness into deflection, you will be getting 16.08 Newton. This load means it is the tension, which is 16.08 Newton. And there is third part, which is the maximum velocity of the weight. Maximum velocity is given by R into omega. R is amplitude, which is 0.08. Omega value, how to find omega? Frequency is given. Frequency is 1 oscillations per second. So equation connecting frequency and omega is omega equal to 2 pi into f. So you will be getting omega equal to 6.28 radians per second. Just substitute over here and you will be getting the final maximum velocity, which is 0.5 meter per second. So that were the basic problems related to spring mass systems. Now let us see if the springs are connected together. Connection means it may be either in series connection or in parallel connection. So let us see the first case, springs are in series. Let us see this figure. Here there are two springs which is connected in series and it is connected to a weight W. Here we can see that this total weight will be carried by each spring. This total weight W is carried by each spring. Now let K1 be the stiffness of first spring and K2 be the stiffness of second spring. Now also we know that this total deflection caused by this weight W will be equal to deflection of first spring plus deflection of second spring. Now let us find an equation for it. We have the equation stiffness equal to W by E, stiffness equal to weight by deflection, that is K equal to W by E or E equal to W by K. Now for the first spring it is E1 equal to W by K1, for the second spring it is E2 equal to W by K2. Now also we have the total deflection equal to deflection of first spring plus deflection of second spring, that is E equal to E1 plus E2. What is E? It is W by K. E1 is W by K1, E2 is W by K2. So W gets cancelled. Finally, it will be 1 by K equal to 1 by K1 plus 1 by K2. Or if the springs are in series, the final stiffness is given by 1 by K equal to 1 by K1 plus 1 by K2. Now, if there are 3 or 4 springs, then also it will be just like this, that is 1 by K equal to 1 by K1 plus 1 by K2 plus 1 by K3 plus 1 by K4. Now if the springs are connected in parallel, so this is the figure for that. Fixed at one end, there are two springs having stiffness K1 and W1. Second spring is stiffness K2 and weight W2. The total weight will be capital W. Now we can see that the deflection for both the springs will be same. That is, E value is same for both. Or we can write it as stiffness equal to K equal to W by E. For the first spring, K1 equal to W1 divided by E. For the second spring, K2 equal to W2 divided by E. Or if you are rearranging it, it is W equal to KE, W1 equal to K1E, W2 equal to K2E. Here we can see that the total weight W equal to summation of these two weights, that is W1 plus W2. What is this W? It is KE. W1 is K1E, W2 is K2E, or E gets cancelled in all these cases. And finally, stiffness equal to K1 plus K2. That is the total stiffness equal to just summation of these two stiffnesses. So if the springs are connected in parallel, it is just addition. And if the springs are connected in series, it is the reciprocal. Now don't get confused between these two. If it is parallel, it is just addition of the spring constant. Here also, if there are 3 or 4 springs, it is Total stiffness will be addition only, that is K1 plus K2 plus K3 plus K4, etc. Okay, let us see a problem. A single problem is sufficient because in this we will be covering both series and parallel connections. And this is a very important problem because it is being asked in KTU question papers many times. Okay, so let us see the problem. A body of mass 50 kg is suspended by two springs of stiffness 4 kN per meter and 6 kN per meter as shown in figure. The body is pulled 50 mm down from its equilibrium position and then released. Calculate the frequency of oscillation, maximum velocity, and maximum acceleration. So these are the figures. This is given in the question itself. First one is series connection. The spring stiffness is 6 kN per meter and 4 kN per meter. It is connected to a mass of 50 kg. Second one is parallel connection. Again, connected in parallel, stiffness is given, mass is given. And third one is another type of connection. This thing we will be seeing it later. These two things we know. It is series and parallel connections. So first case, we will be taking each one. First case, if it is series connection, springs are in series connection. What is the equation for total stiffness? It is 1 by K equal to 1 by K1 plus 1 by K2. K1 is given, K2 is given. Here, first thing to be noted is K1 is 6 kilonewton per meter. Convert into Newton. So it is 6000 Newton per meter and K2 is 4000 Newton per meter. So 1 by K equal to 1 by 6000 plus 1 by 4000. While solving, you will be getting K equal to 2400 Newton per meter. So that is stiffness, total stiffness. Now what we want is, first is frequency of oscillation. So what's the relation between frequency and stiffness? Frequency is 1 by 2 pi into root K by M. So 1 by 2 pi into root K is 2400 Newton per meter divided by mass. Mass is 50 itself. So just substitute, you will be getting 1.103 cycles per second or hertz. Now the second one is maximum velocity and maximum acceleration. So maximum velocity is r omega. R value is, it is pulled by 50 millimeter. So convert into meters, it is 0.05 into omega value. How to find omega? Relation between frequency and omega is omega equal to 2 pi into f. So omega equal to 6.92 radians per second. Just substitute over here, you will be getting maximum velocity as 0.346 meter per second and maximum acceleration as 2.4 meter per second square. Maximum acceleration is r omega square, so you will be getting 2.4 meter per second square. Now, the second case, if the springs are connected in parallel. If it is connected in parallel, what will be K value? It is just addition, K1 plus K2. So it is 6000 plus 4000, which is 10,000 Newton per meter. Frequency, the remaining things are same, just like what we have seen in series connection. So frequency is 1 by 2 pi into root K by M. And maximum velocity is r omega, maximum acceleration is r omega square. So just substitute over here, you will be getting these values. Now what about the third case? What type of connection is this? Series or parallel? Here it is parallel connection. So if it is parallel connection, then what will be the value? Just the values what we got in parallel connection. So these are the values for parallel connection. Just understand this figure is in parallel connection. So the springs are in parallel, frequency equal to 2.25 cycles per second. Maximum velocity is 0.707 meter per second and maximum acceleration is 9.99 meter per second square. So that's all about spring mass model. This is also a very simple topic. Only two additional equations we have studied over here, which is stiffness equal to load by deflection and time period t is equal to 2 pi into root m by k, or in terms of frequency it is 1 by 2 pi into root k by m. Now the other equations like v equal to r omega, a equal to r omega square have been already studied in the last class. So it is not new to you. Anyway, using these equations, you can solve any type of problems from spring mass model. Now let us have a look at what were the portions we covered in module 5. These were the portions which we covered in module 5. First one is kinematics of rotation. We have already studied it in part 1 of module 4, so didn't take it again in module 5. Then rotation about a fixed axis in part 1, rotation under a constant moment in part 2, plane motion of rigid body in part 3 and 4, instantaneous center of rotation in part 5, simple harmonic motion in part 6, and spring mass system in part 7. The link of these video lectures will be given in the description box. Now, one thing to be remembered in examination point of view is, wherever possible, please draw the figures and explain it. Let it be theory or problems, because figures carry marks. If your figure is correct, then you can simply solve the problem. So thoroughly study the modules, don't by heart the problems, just understand the concepts, and then you can crack any problems related to mechanics. And if you have any doubts related to mechanics, you can ask through the comment box, or you can mail me also. The mail ID will be given in the description box. So all the best for the exams. Wishing you a bright future. Thank you.